Hi everyone. Welcome to ILTA Physics Online. Today, we're going to study gravity and the orbital motion that it causes. Since gravity usually refers to the force that acts on Earth or Moon or other planets, let's now widen our perspective and look at it from a universal point of view. According to Newton's discovery, every object in the universe pulls on every other object. There's always an attractive force between them. First, we'll take a look at the physical relationship that describes this gravitational force. Then, using the idea of gravity acting on a freely falling object, we'll learn how to calculate the gravitational acceleration on other planets. Finally, we'll see that when this gravitational force acts as a centripetal force, the object moves in a circular path. We'll organize the equations that describe this circular motion, and that will be the end of today's lesson. All right, let's dive into the universal world of physics. Newton made several important discoveries in classical mechanics in physics about how objects move, the laws of motion. In addition to that, he also made a major discovery about the attractive force between objects. You've probably heard the famous story about Newton and the apple. It's said that while Newton was thinking about gravity under an apple tree, an apple happened to fall to the ground. And that story is at least partly true. Newton's law of gravity was established based on observations like this. He realized that every object in the universe attracts every other object with a certain force. As you can see in the diagram on the right, two objects with different masses exert mutual forces of attraction on each other. That means object 1 pulls on object 2 with a force, which we call F1 on 2. And at the same time, object 2 pulls on object 1 with a force called F2 on 1. The direction of each force is toward the other object. They pull each other inward. This is exactly what we learned earlier as action and reaction forces. They have equal magnitude but act in opposite directions. The magnitude of this gravitational force depends on two main things. First, it's inversely proportional to the square of the distance between two objects. And second, it's directly proportional to the product of their masses. We can express this relationship with the following equation. And here, the constant g is called the gravitational constant, which has the following value. This is what we call Newton's universal law of gravity. One thing to add, the gravitational force between ordinary objects is extremely small. As you can see from the value of the gravitational constant, it's on the order of 10 to the negative 11th power, which is incredibly tiny. However, this force does definitely exist, and when it becomes large enough to noticeably affect the motion of an object, it usually means that one of the objects has an enormously large mass. In the next section, we'll take a look at such cases, the gravitational attraction involving massive objects like the Earth or the Moon. As we discussed earlier, the gravitational force that Newton discovered can actually affect the motion of an object, especially when that object has a very large mass. Now, imagine you're traveling to the Moon in a spaceship, and you decide to measure your weight there. What do you think your weight would be? Your mass, which is an inherent property of your body, stays the same whether you're on Earth or on the Moon. However, your weight, which is the pulling force that a planet exerts on you, will be different depending on which planet you're on. That's because each planet has a different gravitational acceleration. So let's try to calculate the gravitational acceleration on the Moon. First, as shown in the figure on the right, imagine an object of mass m being dropped freely from a height h above the surface of the Moon. In this situation, we can think about two physical laws, both discovered by Newton. First, since the object is moving, Newton's second law, that is, acceleration law, applies. There is a downward force acting on the object, that's its weight. According to the formula F equals ma, This weight equals the mass times the moon's gravitational acceleration. This describes the relationship between force and motion for the freely falling object. Second, both the moon and the falling object exist in the universe. And as we learned from Newton's law of gravity, every object in the universe attracts every other object with a gravitational force. The magnitude of this attractive force is inversely proportional to the square of the distance between them, and directly proportional to the product of their masses, just as we discussed before. If we apply this idea to the figure on the right, the gravitational force that the moon exerts on the object, written as F moon on m, can be calculated using this equation. Here, the distance between the two objects is the radius of the moon plus the height h above the surface. However, because the moon's radius is much, much larger than that small height, we can simplify the expression by approximating the distance as just the radius of the moon. When we simplify it this way, the equation takes on the same form as the one we saw before, the universal law of gravity. Now, these two forces we just described, the weight of the object and the gravitational attraction from the moon, are physically the same force. So if we set the two equations equal to each other and solve for the gravitational acceleration, we get the following expression. By generalizing this result, we can express the gravitational acceleration, or the free fall acceleration, on any planet. It turns out to be directly proportional to the planet's mass and inversely proportional to the square of its radius. This is a very common type of question on exams, so make sure you understand this relationship clearly and memorize the formula as well. Finally, let's think about an interesting type of motion caused by the gravitational attraction of a massive object, like a planet. Imagine there's a small object with mass small m moving around a much larger object with mass capital M. If the large object's gravitational attraction acts as a centripetal force, then the smaller moving object will follow a circular path, performing orbital motion. An object that moves around a planet like this is called a satellite. Now let's calculate the speed of the orbiting satellite. As shown in the figure on the right, consider a small satellite of mass small m orbiting around a much larger body of mass capital M. The gravitational attraction between the two objects can be expressed using Newton's law of gravity as this equation here. When a gravitational force acts as the centripetal force on the small satellite, we can also express it as the mass times the centripetal acceleration. Now, if we set these two expressions equal to each other and solve for the satellite's speed, the green V in the diagram, we get the following equation. This equation has the same form as the one we learned earlier for the slowest speed required to maintain circular motion, what we called the critical speed. The only difference is that the gravitational acceleration term here corresponds to the planet's gravity. All right, now let's find the orbital period of the satellite, the time it takes to make one complete revolution. As we discussed in our earlier lesson on circular motion, the orbital speed can be written as the circumference of the circle divided by the time for one revolution, which is the period. If we square both sides of that equation and rearrange it in terms of the period, we get this relationship. This shows that the square of the orbital period is proportional to the cube of the distance between the planet and the satellite. That's the famous Kepler's third law of planetary motion. So today, we study the gravitational attraction that exists between all objects in the universe. We saw that by applying this force to free fall motion, we can calculate the gravitational acceleration on different planets. And when that same gravitational attraction acts as a centripetal force, a satellite can perform orbital motion, and we can derive its orbital speed and period using the equations we just discussed. That's all for today's lesson. Great job, everyone. See you next time.